Alrighty, welcome back to IET 301, Engineering Project Cost Analysis. In this video, we're going to be looking at Chapter 5, which introduces present worth analysis and goes on to introduce capitalized costs. What we see when we're looking at present worth analysis is that this allows us to consider the present worth or the present value of some scenario. For example, if we want to determine if something, let's say that we're purchasing a piece of equipment, if we want to determine how much that piece of equipment is going to cost us in today's money, given a series of maintenance charges associated with it, and maybe a salvage value associated with it in 5 or 10 years, we can look at the present value of that and of that piece of equipment and use that to determine if it is economically viable. Generally, this present worth analysis is used to choose the best alternative among 2 or more alternatives. If we bring everything into today's money, we can use that to decide which is the best alternative. Now, when we're going through and looking at these analysis techniques, there's a couple things that we have to keep in mind. First off, there are some criteria associated with these alternatives, and these allow us to decide what we're trying to accomplish with the analysis techniques. The first thing that we need to take a look at is a situation when we have fixed inputs. Okay, these are generally associated with the costs of whatever we're taking a look at. If we have an example of an engineer has a budget of $1 million per year. This would be an example of a fixed input. We'll see here in a second that in the case where we have fixed inputs, that is fixed costs, the goal of these analysis techniques are going to be to maximize the outputs, that is, maximize the profits. Okay. The other criteria can be that we have fixed outputs. An example of this may be that a production facility can only produce X number of units per year. In this case, what we're going to want to do is minimize the costs. We're going to, if we can only make so much possible money off of a resource or off of a product line or whatever the case might be, it makes sense that since our output is fixed, we're going to try to minimize the inputs. So in this case, a good example of this is just as a kind of a artificial example, an engineer needs to buy a new computer. We see that in this case, the computer is the fixed output, so we want to minimize the inputs, that is, the cost associated with that new computer. The other possibility or possible thing that we might run into is a situation where we have neither inputs nor outputs fixed. Go down a few lines here. In this case, what we're going to try to do is maximize the profit by maximizing the revenue and minimizing the expenses. So if you recall the problem on assignment number 2, where we had the parabolic revenue function, we saw that the maximum profit occurred not at the point of maximum, or the maximum profit occurred not at the point of maximum revenue, but at some point away from that, because we had to consider the difference between the revenue and the cost. Okay, so an example of this might be So let's say a firm gives back a loan, meaning they have more work than they can handle. They have two alternatives: turn down the work or hire additional staff. Okay. So in this case, they could choose which of the two alternatives is going to be most profitable for them. Okay. So let's take a look specifically at these criteria in terms of what we're trying to achieve. As I've already stated, in the case where we have fixed inputs, we're trying to maximize the outputs. That is the benefits for the scenario that we're working on, or for the alternative that we're looking at. Okay, and I'll actually go up here and say that the goal is to maximize the outputs. Okay, so if we have a situation where we have fixed outputs, the goal is to minimize the inputs. And these are the costs associated with the alternative that we're considering. And then finally, in the third possibility, the goal is going to be to maximize the present worth, the net present value. And we can say that the net present value is equal to the sum of the benefits minus the sum of the costs in this scenario. Okay, so as I've already mentioned, in this case we're going to be doing nothing more than trying to bring everything into the present value so that we can go through and analyze the situation to determine which is the best alternative. And when we go through and take a look at some of the problems we'll encounter, we kind of have to recognize what we're trying to achieve when we look at the problem. So as an example, let's look at an example. And in this example, what we see is that we have, give it a second here, we need to go through and choose between two alternatives. We have two machines that we have to consider buying. They both serve the same purpose on the production line, they just have a different cost associated with them. In this case, since we're considering the cost of this piece of equipment, our goal is going to be to minimize the cost. So as we go through here, we have machine X has an initial cost of $10,000, a maintenance, specifically an annual maintenance of $500 per year, and no salvage value. That means that at the end of its life cycle, essentially we're going to have a piece of equipment that we're scrapping, we're throwing away, we're turning it into landfill material. So in this case, our first alternative, I'm going to draw two columns here since there are two alternatives. We know that alternative A is referring to machine X. Based on the description, we have an initial cost. Keep in mind that that's a fixed cost of $10,000 and a variable cost. This is in the form of our maintenance cost of $500 per year. Okay. At the end of its 4-year lifespan, it's not worth anything. So salvage value is 0, and lifespan, or life cycle, whichever you want to refer to it as, is 4 years. Okay? So what we could do right now is go through and find the present value of this investment over the 4-year term. However, before we do so, let's go ahead and read the rest of this problem. So we see that the other alternative is to purchase machine Y. So machine Y has a $20,000 initial cost. Let me write it out in the same format as I did, of $20,000. We have no maintenance cost the first year, but a gradient starting at the beginning of the second year. So this means that we have a gradient of $100 per year starting in the second year. The life cycle of this piece of equipment is 12 years, and at the end, we have a $5,000 salvage value. So what we're going to see is that the salvage value is $5,000, and that really doesn't look like salvage. There we go, that's a little bit better. And the life cycle is 12 years. Okay, so the question becomes then, hey, look at this. We've got machine X with a life cycle of 4 years, machine Y of a life cycle of 12 years. Now, if we were to go through and look at the present value of this piece of equipment, sure enough, we could go ahead and look at it over a 4-year cycle. That would be great. That would give us the present value of that piece of equipment. But would that present value reflect or represent the same cost associated with machine Y? And the answer is no. One of the key things you always have to do is make sure that anytime you're analyzing using this present worth analysis tool, that you're analyzing over the same period, okay? In this case, since the periods are different, we would have to go through and figure out some way to look at this analysis over the same interval of time. And so what I'm going to do is I'm going to say, okay, well, since 4 is easily goes into 12, I'm just going to analyze this over a 12-year period, because 4 times 3 is 12. And that means that I'm going to be looking at machine X over 3 cycles, okay? That means that we're going to replace machine X 3 times to represent the life cycle of machine Y. So let's go through and think about the present value of just the initial cost of the equipment. We can see that in year 0, we have a $10,000 investment. Keep in mind, present worth analysis, we're bringing everything into present value. That means we're determining how much money we would need today in order to pay for this for the full life of the project, okay? So today, if we were to go out and purchase this piece of equipment today, we would need $10,000 to pay for it for the first 5 years. I'm sorry, for the first 4 years. At the end of that 4 years, we would have to replace it. So we would need another $10,000. And we know that we're trying to figure out the present value of some future sum. So we're going to use the P given F formula, add 8% interest, because that is given in the problem, 8% interest, and this first tool is going to be replaced in 4 years, okay? After that, we would need to go through and perform the same calculation again. We're going to have to figure out the present value of some future investment at 8% interest after 8 years, because the tool is replaced at the end of the 4th year and at the end of the 8th year. It only has a 4-year life cycle. So that means that the present value of the cost of the equipment is going to be $10,000 plus 10,000 times P given F of 8% for 4 years, plus $10,000 times present given future of 8% for 8 years. Okay, so from my tables here for 8% interest, let me bring them up here. These are actually from a different source, so they're referring it to Appendix B. In fact, in our textbook, we know that the tables are in Appendix C, so just kind of bear with that. But we see that on the 8% table, we are looking in this first case for the present given future value, so P given F, that's the second column here, and we're looking for the fourth entry. The fourth entry is 0.735, okay? I'll just go ahead and highlight the eighth entry too, which is 0.5403, because we in fact need both of them. So what we see is that we have $10,000 plus $10,000 times the multiplier for present given future at 8% for 4 years, which was 0.735. Oops, that's way off the page there, sorry about that. Plus $10,000 times the multiplier from the table, which was 0.5403. So we see that in order to be able to purchase the equipment, we would need $10,000 for the first one, $7,350 for the second tool, and then $5,403 for the last tool, which gives us a grand total, let me grab my calculator here, of $10,000 plus $7,350 plus $5,403 gives us a grand total of $22,753. Now this only represents the cost to purchase the equipment. It doesn't factor in the maintenance associated with this. So in order to figure out the variable cost, we would have to go through and do the same thing. In this case, though, we're considering a uniform series, so we're going to have to say that we have an annual maintenance cost of $500. We are trying to find the present value given an annual contribution at 8% for the full 12 years. Keep in mind that we could run this for each of the terms. It would be 500 times present given annual of 8,000, 8% for 4 years times 3, or actually that wouldn't quite be right, because then we'd have to find the future value of this and use that future value to calculate the next, and so on and so forth. So in this case, we see that the maintenance cost is going to be a gradient, it's going to be a uniform series. So we're going to have a $500 maintenance cost per year for the full 12 years, and that gives us from the table, for the 12 years, we're looking for the present value of a annual contribution, which is right there. We see that our multiplier is 7.536. So we would have 500 times 7.536. And so our total cost of the first alternative is the $22,753 plus the, 500 times 7.536 to give us $3,768. That means that our total cost of this alternative is $26,521. Okay. That means that if we choose alternative A, what we would have to have is $26,521 in the bank today in order to fully pay for this over the 12-year life cycle. Okay? So let's go through and do the exact same thing with alternative B. Okay? Now, one thing that you will see is that when you're working with these problems, they tend to have, each of the alternatives don't necessarily have the same level of complexity. For example, you'll see that the first alternative for machine X tends to be a little bit more involved. However, for machine Y, we know that we're running for the full 12 years, and therefore the initial cost to purchase the equipment is just the $20,000. That is already in today's money, okay? So we can just say that we have $20,000 that we need to have available today to buy this piece of equipment. Job done, okay? The variable cost is going to be represented by this gradient, okay? So we're going to say that the variable cost is going to equal to $100, and we're going to turn that gradient into a present value, so we're going to do a present given gradient at 8% interest for the 12 years. Okay, so once again from our table, we're going to say that we're looking for the present given a gradient, so that is over here, at 8% interest for 12 years. Our multiplier is 34.6339. So 34.6339. And so the variable cost associated with this is $3,964. I'm going to round this just because we don't need that little bit of change there. Okay. Now, the final thing that we have here, did my mic stop working? I think my mic stopped working here, so. Okay, so it looks like the batteries are just about dead on my microphone, so I will make sure that they are replaced by the time I do the next video. So I'll just try to speak up as best I can. So what we have here then is one final consideration that we need to make, and that is the salvage value of this other alternative for machine Y. So in order to consider that salvage value, we need to bring that future value back into present value. So that means that we're going to take the $5,000 and find the present value of it. So we have a future value that we're, or a present value that we're trying to find given a future value. Again, that's at 8% interest for the 12 years, okay? So from our table, we see that in this case, we have a present given future. So our multiplier from the table is 0.3971. So we have $5,000 times 0.3971. And when we go through and punch that into our calculator, we have 5,000 times 0.3971, meaning that we have $1,985 in today's money associated with that salvage value. Okay, so let's put this all together. We see that the initial cost of $20,000 is truly a cost. We see that the variable cost for the maintenance is definitely a cost. But notice that this is money that's coming back into our pocket. So it would counteract this $20,000 here and this $3,964. So we could say that the total cost associated with this scenario is equal to the $20,000 plus the $3,964 minus the $1,985. So punching this in my calculator, we have 20,000 plus the 3,964 minus the 1985, and that means that the total cost of this scenario is $21,979. So from this, we can see that machine X is going to cost us $26,000, a little over $26,000 in today's money. Alternative B, which is associated with purchasing machine Y, is going to have a value of $21,979 in today's money. Therefore, it would be most beneficial to choose machine Y because it has the lowest present worth associated with the cost of that piece of equipment. Okay, so this gives you a really good idea of how to set these problems up. Not all of these problems are necessarily this involved, but I can guarantee you that every one of these present worth problems and every one of these analysis problems that you do is definitely going to involve going through and considering multiple alternatives, and therefore going to require analysis, as we have done here, of the different alternatives. So essentially, every one of these problems is going to represent two problems, or I should say two or more problems in one. Okay, so let's take a look at a second example real quick. And after that, we will be nearly done with this discussion. So let's go through and take a look at this alternative. We can see that in this case, we have both a cost and a series of incomes. Therefore, our goal is going to be to maximize the net return on this investment. And let me zoom in just a little bit here. Okay, so in this case, we've got two alternatives again, so I'm going to go through and just put a line straight through the middle so I can analyze alternative A, analyze alternative B, and then choose the best of the two alternatives from those. Okay, so in this case, we're going to be maximize the, let's see, what did they call that? The net present worth. That means that we're going to take the sum of the benefits and subtract it from the sum of the costs, okay? So what we can see for alternative A is that we've got a cost that's already in today's money. This is $2,000. Remember, if it's in parentheses, it means that it's a negative or a negative cash flow. Okay, and then we have some benefits. Okay, the benefits represent a uniform series, meaning that they have the same amount associated with them each year. So we can say that the net present value is going to equal the sum of the benefits minus the cost. Okay, and I should say, if I'm representing this as a negative, it would be benefits plus costs, because the negative would be already built into the problem. But in this case, we can say that in order to account for the benefits, we're going to have $800. We're trying to bring that $800 back into present value, and it represents an annual contribution. In this case, the problem says that we're dealing with a 5% interest rate for 3 years. Okay. And from that, we're going to subtract off the cost of this alternative, the $2,000 that we're contributing, that we're throwing at this alternative. So in this case, we can see that the net present value will be the $800 from our 5% table. And again, this table is from the internet. I found it on the internet instead of having to dig through and find our appendix C each time. So I can see that on the 5% table, we are looking for the present given annual. So present given annual for 3 years. So our multiplier is 2.723. So our multiplier is 2.723 minus the $2,000. Therefore, the net present value of this investment is 800 times the multiplier of 2.723 minus the $2,000 to give us a net present value of $178.04. That's how much this alternative A is worth in today's money. Okay, doing the exact same thing with alternative B. I'm going to go through and say that the cost is $2,800. The benefits, again, is a uniform series, so we're going to take the $1,100 times, let's see, we're trying to find this in present value given an annual contribution at 5% for the 3-year term. And so we see that our net present value is equal to the $1,100 times, you'll notice that the multiplier is the same. The multiplier is the 2.723 because we're analyzing this over the same interval minus the $2,800, and therefore the net present value is the 1,100 times 2.723 minus the $2,800, and we have a net present value of $195.30. So from this we can see that alternative B is the most beneficial. It maximizes the net present value of the two scenarios. So in this case, it would be better to invest $2,800 today with an annual return of $1,100 versus investing $2,000 today with an annual return of $800 for the next 3 years. Okay, so with this then, that gives you a real good idea of what you're going to be taking a look at in Chapter 3. So let's talk about just one more topic in this chapter, and that's the topic of capitalized cost. Okay, so in a number of situations, such as long-term maintenance of highways and bridges and dams and so on and so forth, we have considered the situation when our investment period is assumed to be infinite. Okay? That means that we're wanting to maintain this bridge or this road or dam or whatever the case is until society and civilization no longer exists. We want to make sure that whatever happens, we have the money for that infrastructure investment. Okay? So in these situations, what we want to do is consider the capitalized cost. And what we're going to do is invest enough money into an account so that any recurring cost, either to replace the equipment or the bridge or highway, along with any maintenance associated with that infrastructure, is accounted for. So if you want to think about it, if we have a project that costs a certain amount P, and sometime in the future we have earned a fixed interest rate that gives us a new principal balance, P plus PI. We could then take that PI off of this initial investment and use it to replace or maintain that bridge or highway. And then we could go through here. In this case, we're going to be taking off the capitalized interest that we've set aside and be collecting interest just on the principal amount again. That means that over T years here, 2 years here, we will again have the principal plus the principal times the interest. And again, we can take that principal plus interest off, and in this way we can maintain this capital investment indefinitely. Okay? Well, it turns out that if we want to go through and determine how much cost what the present worth of an infinite investment is, this is what we're referring to as the capitalized cost. And this turns out to be a very easy calculation. We can say that the annual contribution, and keep in mind that this annual contribution in this case would probably not occur annually. What we would have to do is recognize that this is capitalized over a long term, maybe 30 years or 40 years, or however long the service life for that particular road is. It's going to be equal to nothing more than the principal times the interest. So from this then, we can find the present value as the annualized return divided by the interest rate. Good. And that's all there is to work with when we're considering the the capitalized cost. So as an example, if we have a situation where we have annual maintenance of $7,500. In this case, I have a annual contribution, happens to be annual maintenance cost of $7,500, and we happen to have our money invested in an account that's earning 5%. How much do we need to have in that account to sustain this annual maintenance forever? Well, in this case, we could say that the present value would have to be the 7,500 divided by 0.05, and in this case, the $7,500 divided by 0.05 would mean that we'd have to have $150,000 in that account in order to be able to maintain $7,500 maintenance forever. Okay. If we start suddenly requiring $8,000 in maintenance, this would no longer be valid because our principal amount would start to decline, and therefore we would not be able to maintain this project forever. So this should give you a real good idea of how to set up the problems for Chapter 5. And as soon as I get the batteries replaced, I will go through and record and post the overview of Chapter 6. Chapters 5, 6, 7, and 8 all talk about different analysis techniques, meaning that you're going to be using these analysis techniques to choose the best of several alternatives. So I hope this has helped. If you need any help on the assignment, feel free to give me a hand. A few of you have been doing so. And I will talk to you later.